Hi everyone, welcome to this M2D2 talk. Today's speaker is Professor Jian Tang, and his talk is about predicting geometry. It's about how to use the geometry deep learning and apply that to drug discovery. Professor Jian Tang is currently Associate Professor at Miller Quebec AI Institute and the Computer Science Department and Business School of University of Montreal. His main research interests are graph representation learning, graph neural networks, geometry deep learning, deep generative model, knowledge graph, and drug discovery. He was awarded multiple times the Best Paper Award at top-tier conferences, including ICML and the Top Data Mining Conference World Wide Web. He was also awarded the Amazon and Tencent Faculty Research Award. He is one of the most representative researchers in the growing field of graph research, graph representation learning, and has published a lot of seminal work in that field. Recently, his group has just released an open source machine learning package called TorchDrug, aiming at making AI drug discovery software, aiming at making AI drug discovery software and library freely available for everyone. Thank you so much, Prof. Jian Tang, for accepting our invitation to present today, and looking forward to your talk. Before we start, a note to everyone, if you have any question, please raise your hand, and when Prof. Jian Tang will feel it's best to take them, he will let you speak. Thank you.
Okay. Can you guys hear me?
Yes.
Okay. Thanks for the invitation and also introduction. It's a great honor to speak here. So I'm actually now in China. So it's 11 p.m. In China now. So I will try to stay awake. Okay. So I'm going to talk about like geometric deep learning for drug discovery. So you can also like say graph neural networks or graph representation learning for drug discovery. So my group has been working on this like since 2018. So in today's talk, I'm going to share some our most important progress in this direction in the past like 4 years. Okay. So I will start from a simple maybe. So I will start from a brief introduction to drug discovery. So in general, you know, like drug discovery is a very long and expensive process. On average, it takes more than 10 years and also costs like $2.5 billion to develop a new drug. So a typical process of like drug discovery is like this. Suppose you have like a disease, let's say SARS-CoV-2. So in the first stage, we have to identify a drug target. So most of the time, the drug target is a protein. For example, for SARS-CoV-2, the drug target is a spike protein, right? And then once you have a target, then so we're gonna get into the stage of drug discovery. Okay, so in the stage of drug discovery, so we're gonna identify a few molecules, like which, for example, which could bind to the protein target, which could also have other good like biophysical properties, right? And then for those molecules, we're gonna evaluate them in the preclinical stage. Most of them we're gonna evaluate them in the animals, for example, in the mouse, in the rabbits, right? And then once those molecules can pass the preclinical stage, we're gonna evaluate those molecules through like clinical trials. So most of the time we have 3 different stages of clinical trials, right? And then once they are able to pass the clinical trials, so they can get approved. So in general, the success rate of passing the 3 phase of clinical trials is very low, which is around like 10%. And that's why nowadays we are very interested in using AI to increase the success rate of drug discovery in this drug discovery stage. Of course, we also want to accelerate this process. Okay, so now we are basically okay, and we are witnessing a big opportunity for using AI to accelerate the process of drug discovery and also, of course, increase the success rate. Because nowadays we see a huge amount of data is generated in the biomedical domain. For example, we have a huge amount of like scientific literature. So we have a huge amount of like public data sets, for example, the PubChem data sets, and also the PDB data set, which is used to train the AlphaFold model, right? We also have a lot of like clinical data, and also a lot of data is generated through high-throughput assays, right? So by using AI to analyze those huge amount of data, so we can extract patterns. So we can generate hypotheses, we can make predictions. For example, based on all this data, we can make predictions, we can predict the properties of the molecules, and then we can select molecules which have good properties, for example, have good binding affinities, and also, good biophysical properties, right? And those molecules are more likely to succeed in the clinical trials, okay? So talking about data in this domain, so what are the most important data in this domain? For sure, they are drugs. So drugs can be small molecules and also proteins, right? So for small molecules or proteins, for each of them, they can actually be represented as graphs. For example, for small molecules, so they can actually can be represented as a graph of atom, right? So every atom is a node, and the bonds between the atoms correspond to the edges of the graph, right? Or between the nodes. So that's how you can represent a molecule as a graph. So the same case, like actually you can also represent a protein as a graph, right? So every node, every residue is a node. So the special relationship, for example, the distance between the residues in the 3D structure correspond to the edges between the nodes. Okay, so that's how you can represent a protein as a graph. Okay, of course, instead of like representing molecules and proteins as a graph, so another way to represent the two type molecules is to directly represent them as a 3D structure, right? So in this case, every atom or every residue can be represented as a 3-dimensional coordinates. And that's a different way to represent small molecules and proteins. Okay, so that's one type of data, molecules and proteins. Okay, and that's a single graph, a single 3D structure. So another type of like very important data, which is not a single molecule, but instead is actually the interactions between the molecules or the interaction between molecules with other biomedical with other biomedical entities. So this is actually known as biomedical knowledge graph. So here I give you one example. So which is a biomedical knowledge graph of disease, drugs, and the genes or proteins, right? So you can see that this biomedical knowledge graph basically encode complex relationship between different kinds of like biomedical entities. For example, here we have like a relationship between a drug and the disease, basically, okay, to see okay whether this drug can reduce the effects of this disease, right? Whether there's a causal mutations between this gene and this disease, indicating that okay, this gene is actually can be a good drug target for this disease, right? So biomedical knowledge graph is actually very important in a bunch of like applications in drug discovery. So let me give you some example. So based on this biomedical knowledge graph, if we can predict, okay, there's going to be a link between a drug and the disease. So this means that, okay, this drug potentially can be used to treat this disease, right? So this actually is very important for applications like drug repurposing, okay? Or let's say we can predict there's going to be a link between this gene and this disease. So this means that okay, this gene or this protein can be somehow actually be a potential drug target for this disease. Okay, so you can see that either for those like small molecules, proteins, or the biomedical knowledge graph, so they can be easily represented as a graph, small graph or big graph, or a single 3D structure. So in a case, you can see that. So in order to use deep learning techniques to analyze those data sets, so we need to rely on techniques like graph neural networks or geometric deep learning. And that's why graph neural networks or geometric deep learning have huge potential in drug discovery, because you can see most of the important data in this space are related to graphs or 3D structures. Okay. So in today's talk, I'm gonna mainly cover 3 parts. So in the first part, I'm mainly gonna cover like how can we use like geometric deep learning to analyze a single molecule, a single protein. So I'm gonna cover like a traditional, more like graph-based methods, mainly based on like graph neural networks. Okay, and also we'll cover some recent progress based on 3D structures. So here we are mainly cover like methods based on geometric deep learning. Okay. And then in the second part, I mainly cover like another kind of like another type of data, which is biomedical knowledge graph. So this is a very big graph, right? As I said, so this has huge applications in cases like drug repurposing and also target identification. So finally, I'm gonna briefly introduce two, or actually a unified system that developed in my group, which is called like TorchDrug and TorchProtein, which is basically a very general machine learning system for drug discovery for both small molecules and proteins. Okay, so we're gonna start from the first part, molecule and protein modeling. So as I said, like in the beginning, so my group has been working on this since 2018. So we actually have been working on a bunch of like important problems for drug discovery. So for all these problems, we mainly study molecules. So we represent molecules as graphs, and then we use graph neural networks to analyze those graphs, right? So the first fundamental problem we work on is molecule property prediction. So basically, the problem here is like, given a molecule or a compound, we want to predict its property, for example, binding affinity or toxicity, right? So the fundamental machine learning problem here is, how can we learn a good representation of a molecular graph, right? So that we can predict its property. Okay. So specifically in this direction, so we have been working on like some like self-supervised learning or pretraining methods for this problem, because you know, like in drug discovery, so one of the most important actually challenging problem is that you do not have many labels, because you know, in order to get the label of a molecule, you need to do you really need to do some wet lab experiments, which is very time consuming and also expensive. And that's why I think in drug discovery, actually really promising direction is how can you build like pre-training methods or self-supervised learning methods for learning good molecule repetitions. Okay, so this is one direction we have worked on in the past. And the second problem is de novo molecule design and optimization. So basically in this task, our goal is trying to find a molecule with good property, because you know, like for drug design, the end goal is, okay, you want to find a molecule with good property, which can bind to the protein target, has low toxicity, as well as some good biophysical property as well, right? So in this task, so we've been using techniques based on deep learning models and reinforcement learning. For example, we can first use deep learning models to generate some drug-like molecules, and this is the first step. Of course, that's not our ultimate goal, because once we are able to generate some drug-like molecules, we need to further find some molecules with good properties, and that's why in the second stage we're gonna further use reinforcement learning based technique to search for molecules with good properties, right? And the properties we want can be defined as some reward function, and this is the second type of problem we have worked on. And then once we have identified a good molecule structure, let's say this molecules structure we already identified with good properties, and this molecule structure in practice, I mean, usually it doesn't exist in nature. So the next problem is like, how do we make this molecule, right? Or how to synthesize this molecule in practice? And this is known as a problem called like retrosynthesis prediction. Okay, so basically, okay, given the design, the molecule structure, how do we identify a few existing molecules or a few existing reactants based on which we can synthesize or we can make the molecule we want. Okay, so you can see that for all these problems is actually to molecules, right? And that's why I say, okay, we're gonna use graph neural networks to analyze molecules and then combined with different kinds of techniques for example, based on self-supervised learning, pre-training, deep learning models, and reinforcement learning for different applications in this space. Okay, and that's what we have work on in the beginning. Okay, and then pretty much starting from last year or maybe one and a half year ago, we actually realized some limitations for this kind of graph-based methods, because we realized that for molecules, actually, instead of representing molecules as 2D graphs, we realized that actually a better representation is to represent molecules as their 3D structures or 3D conformations, because the 3D structures of molecules determine their biologic and the physical activities. For example, how they interact with other molecules. Okay, and that's why. So we gradually move from representing molecules as 2D graphs to representing molecules as 3D structures. Okay, of course, there's also a challenge for this direction, because for many molecules, or for most molecules, we actually do not know their 3D structures, right? And that's why nowadays there's a lot of work around this. I believe most of you have already heard the AlphaFold 2 revolution, right? So AlphaFold pretty much is also solving the same problem. So given a big molecule like protein, right, we want to predict the 3D structure of proteins. So we actually work on the same problem, not the same problem, similar problem 2 years ago, before AlphaFold 2 came out, but we didn't work on proteins, but instead we made it work on small molecules. So basically, this is basically the AlphaFold 2 version in computational chemistry, right? So mathematically is defined in this way. So given a molecular graph, we want to predict the 3D structure of this molecule, right? So from the point of machine learning, so essentially we try to model this conditional distribution given the input molecular graph. What is distribution of the conformation of this molecule, right? So a big challenge for this problem is that you can see that for the molecular conformation, it actually satisfies a property, which is that the molecular conformation or the 3D structure of a molecule is actually its rotation and the translation invariant, which means that, okay, if you rotate and translate this molecular conformation, of course, the coordinates of the atoms will change, but it remains to be the same conformation, right? Okay, and that's some inductive bias you need to build in your model. Okay, so in my group, so we actually have been working on this problem for like maybe 1 year and a half. We actually have been developing different kinds of deep learning models for this problem. So in today's talk, I'm going to talk about our latest work for this problem, which is based on the diffusion model. Okay, so this work is published in this is iClear. Okay, so this is the work GeoDiff, geometric diffusion model for molecular conformation. So I want to emphasize, so this is actually the first diffusion model that has been developed on molecules. Okay. So the essential idea of this GeoDiff model is, so we want to model the 3D molecular conformation generation problem as a diffusion process. So it works in this way. So for diffusion process, you have C0 is your data distribution. So in particular here, this is just the molecular conformation. And then, so CT is basically the noise distribution. So here, most of the time, the noise distribution is just a Gaussian distribution, right? So this is a base distribution or noise distribution. And then in the diffusion model, there are two processes. So one process is a forward process, which is from C0 to CT, or you can say from the data distribution to the node distribution. So what we do here is basically, okay, in every step, we're going to add some noise. Okay, you just like add some noise to the coordinates of each atom. Okay, but how do you add noise? So the forward process is actually determined by this Q distribution. As I said, in every step, we're going to add some noise to each atom, and this process is actually fixed. So we do not have any parameters to be learned in this forward process. Okay. So what we really need to care about is actually the reverse process or the journey process. So for the reverse process or journey process, it works in this way. So we sample a noise from this noise distribution, right? And then at every step, for example, from CT to CT-1, so what are we going to do? We're going to enumerate the noise, right? We're going to do the denoising. So we're going to enumerate the noise from CT, so and then we can recover CT-1, okay? And so we do this at every step, and then as in the last at the end, as end, we can recover the ground truth molecular conformation. So this is known as the forward process, or this is known as the reverse process or journey process. Okay, and this is something we need to learn. Okay. So we can formulate this more formally with some mathematical notation. So as I said, in the diffusion process, okay, so diffusion process is defined by this Q distribution. So this Q distribution, so there are no parameters to be learned. So this is just like we just add some Gaussian noise at every time step, right? And then in the reverse process or in the journey process, so it's determined by two distribution. So one distribution is PCT, which is noise distribution. So how do we define the noise distribution? So another distribution is the denoising process, right? How do you go from CT to CT-1? So this is defined by this distribution. So remember that here we always like condition on the input the molecular gravity, right? Okay, so once you have the PCD and this denoise process, and then you can define the journey process. Okay, of course you can see that by far the two process is actually so this is the same process, the same equation. If you apply diffusion model to any kinds of data, right? Even you have image data here, the equation here is the same. But as I said, for this problem, the unique challenge is that the molecular conformation is rotation and the translation invariant, which means that, okay, if you rotate and translate this molecular conformation, the probability should remain the same. So which means that, okay, so the marginal likelihood of this of the data likelihood. So this distribution, of course, this distribution is induced by the generative process, right? Or by the reverse process. So this marginal distribution induced by this generative process should satisfy the property I mentioned in the beginning. It should be rotation and the translation invariant. In other words, it should be SE3 invariant. Okay, and that's something we must need to take into consideration, or it's kind of like inductive bias we must build in the model, right? So in our paper, we have a proposition. So I will not go into the details, but basically here's the intuition. So if you want to make sure, okay, this marginal data likelihood is rotation and translation invariant, basically, okay, you just need to satisfy two conditions. Okay, so one condition is that, okay, the noise distribution PCT should be rotation and the translation invariant. In other words, in this noise distribution, if you rotate and translate the structure, the probability should remain the same. Okay, and that's one condition. Another condition is, okay, in this denoising process from CT to CT-1, So this denoising process should be rotation and translation equivalent. So in this case, it's not invariant anymore. It should be rotation and translation equivalent, which means that, okay, if you rotate and translate CT, so the output CT minus 1 should be rotated and translated accordingly. So if you satisfy the two conditions, then we can prove that, okay, so the marginal distribution you induced by this journey process is rotation and translation invariant. Okay. Of course, the next question is like, how do you define the two distribution PCT and this denoising process, and each of them? So PCT is the rotation and translation invariant, and this denoising process is rotation and translation equivalent. Okay, so here let me give you a little bit more details. Okay, so for PCT, this is not distribution. So I mean, not usually. Because the conformation is continuous variables, right? So usually we can simply use like Gaussian distribution. So like for Gaussian distribution, it's actually rotation invariant, right? Because in Gaussian distribution, if you rotate the structure, so it should be the probability will not change, and that's good. But for Gaussian distribution, of course, it's not. It's definitely not like translation invariant, because if you translate the structure, for example, you stay away from the mean of the distribution, of course, the probability will not remain the same. Actually, the probability will remain, will become smaller, right? So what if we do here is like, okay, what if like at every time we just like we just normalize the structure, the mean of the structure to 0. So in this case, like when we calculate the probability of this structure, it will always be normalized to the 0 mean, right? So in this case, it should be also like a translation invariant, and that's how we are able to define a rotation and a translation invariant prior distribution or noise distribution. Okay, and then so this is the first condition, how we parameterize the base distribution or noise distribution. So another condition, I said, like this denoising process should be rotation and translation equivalent, or SE3 equivalent. Okay, so here we actually propose some SE3 equivalent graph networks. Okay, we are not going to details because nowadays I think so recently, especially starting from last year, there already have been many like SE3 even SEN equivalent graph neural networks, right? So the techniques we propose here actually is quite rated or similar to those techniques, and we will not go into the details. Okay. So here, let me show you some results. So we evaluate our models on two benchmark data sets. So just like this QM9 data set is a data set where the molecules in the data set are relatively small, right? For example, for those QM9 data set, like for each molecule, maybe we have around like 10 to 20 atoms, right? And then for this drug data set, the molecules are relatively larger. For example, we could have like 30 or 40 atoms in each molecule. So you can see like for GeoM like QM9 data set, so our models are already like performing much better than those like baselines, right? So all these baselines at that time, they were state-of-the-art methods for this problem. But you can see like actually you can see that the performance improvement are really much bigger on the large molecules, right? You can see traditionally this one is like 60, and now we can pretty much get a 90, right? So showing that like for those like more challenging data set like big molecules, so our model are able to perform much better than traditional methods. Okay. So here let me give you some examples. Like here are the different input molecular graphs, and then okay. So I see maybe you raise your hand. Okay, maybe there's some question there.
Yeah, there has been one question in the chat, but yeah, you can go ahead and take it afterward. Thank you.
Okay. So Yunchao Nancy Liu asked a question. In the image forward diffusion, it's unsuitable to add Gaussian noise as there's no constraints on the pixel values, but the forward diffusion for coordinate, how do you ensure some geometric constraint at triangular inequality? I mean, so I think we do not need to add some geometric constraints, right? Because our goal here is just trying to really destroy the regular molecular structure into some noise, right? So in the noise case, basically, okay, so, a set of like point clouds, we do not need to ensure the triangular inequality anymore, right? Because we just need to like we just need to change the coordinates of the atoms into random positions. So in this way, the structures of the molecule will be destroyed, right? And then
I have one question to like, can you comment on the speed of those methods compared to maybe using like traditional computational chemistry package, like, because like one of the things with conformal generation is the speed at which we can generate new conformants.
Right. Good question. I think that the traditional method for this forming is actually based on some like force field based method, right? So I think in terms of efficiency, I think that they're comparable. Of course, for diffusion based method, so there's some challenge in terms of like inference, because you know, like for diffusion based method, we usually need to do many diffusion steps in order to converge to the eventual the final stable. For example, in this case, conformation. For example, we need to have like 5,000 in our experiments. Like most of the time, we use like around like 5,000 diffusion steps in order to converge to the stable conformation. So in that case, like it could be a little bit slower than traditional force field-based methods, but note that actually there are also a lot of recent work in the machine learning community, because you know, like diffusion based method is so popular, not only in molecules but also in images, right? In images, and as well as in other domains, and people have been actually trying to increase the inference time of diffusion models. For example, nowadays we don't need to do 5,000 diffusion steps. So maybe we can only do like 10 or 100 diffusion steps. So in that case, we can significantly increase the inference time. So in that case, maybe we are pretty much comparable to the efficiency of traditional force field based methods, right?
Okay, perfect. Okay. Thank you.
So here are some examples, like so here a bunch of like input molecular graph, and then so for each molecular graph, we actually generate quite a few different conformations for this input molecular graph, because you know, like for each molecule we could have quite a few stable conformations, or a few stable structures for this molecule. Okay. So there's a question in the, I think there's no best 3D structure for a molecule. That's true. For example, 3D structure molecule can be the best when integral, but not with. So how you evaluate your model? I mean, how do actually? So in our evaluation, so we actually for each molecule, we actually could have like multiple stable conformations, right? And then what we do is like basically the intuitive works in this way. You can see in the example. Okay, let's say here we have an input molecular graph, so we're going to generate multiple conformations like for this molecular graph, and then what we're going to do is we're going to compare this set with the ground truth conformations, which is also a set of like conformation, right? And then we use some metrics based on precision and recall, and that's how we do the evaluation. Yeah, you are totally right. Good question. So so here The ground truth confirmation in our data set is not the binding confirmation. Yeah, I think Shenyang's answer is right. If we didn't use the binding confirmation. Of course, I think that later I had a discussion with someone else, and then potentially we can also try to predict the binding confirmation. But theoretically, yes, we can do that. But in our experiment, we didn't use it because we use the Jian data set. So I don't think they use the binding confirmation. Right. So, and here we also have a visualization to show how our algorithm works. So you can see that in the beginning, you can see in the beginning all the atoms are randomly placed, right? And then in each diffusion step, we're gonna do denoising, right? Basically, we're gonna move the atoms around to denoise the noise in the coordinates until at the end you can see that all the atoms eventually will converge to the positions of a stable conformation. Okay, and that's intuitively how the diffusion model works in practice. Okay. Any question and other questions before I move to the next part? Okay, so you can see so by far you can see all the work I have introduced actually on small molecules. Okay, so starting from last year, we also actually in my group I also made some big shift in my group. So instead of working on small molecules, starting from last year, we actually also started to investigate a lot of efforts on proteins, on big molecules and proteins. Okay. So one project I want to briefly mention here is how can we learn a good protein representations? Okay, so learning a good protein representations is really important in many tasks. For example, predicting the functions of a protein, right? Okay, of course, so in the current literature, there are already many work for learning good protein representations, mainly based on pre-training methods or self-supervised learning methods. And for proteins, actually a very easy and also natural representation is based on their amino acid sequence. So in other words, we can represent proteins as a sequence, right? And then in this case, a very straightforward solution for this problem is actually we can make use of the techniques we develop in natural language processing. So those bird model, those pre-training models based on bird, right? So we can pre-training a bird model on a huge amount of protein, on a huge amount of protein amino acid sequence. And then so this is usually known as protein language model. And then once we have the pre-trained protein language model, so we can further fine tune the model based on a limited number of lab data. Okay, so all these kind of techniques pretty much are borrowed from what we have in natural language processing, basically pre-training and fine-tuning on a sequence with transformers, right? Okay, so in this project, so what we did is, okay, so instead of pre-training protein repetitions based on sequence, so we propose to pre-training protein repetitions based on their 3D structures, because for proteins, so their 3D structures actually determine their functions. So therefore, a better repetition to learn protein structure is based on their 3D structures. Okay. So what we did is actually we make use of a huge amount of protein 3D structures based on the structures in PDB or the AlphaFold to predicted structures, because nowadays actually we have really a huge amount of predicted protein structures in the AlphaFold 2 database. I think we have maybe a few billions out there, right? And then we propose some self-supervised learning techniques on these protein structures. So let me give you maybe a quick idea on how it works. So let's say now here we have a 3D protein structure, and then what we do is, okay, we're gonna first construct a graph a residual graph out of this protein 3D structure. So every node here is a residue. Okay, and then for the edges between the residues, they could be the distance between the two residues in the 3D structure, or they can be simply some sequential relationship between the residues in the sequence, right? For example, in the sequence, maybe these two residues there, so they're next to each other, right? So we could build an edge in this residue graph. So basically, you can see, so we can actually construct different kinds of like edges from the 3D structures as well as the sequence. Okay, and then once we have this residue graph, so we can actually define a bunch of different like self-supervised learning techniques. For example, we can also define a similar mask language model type of like task on this graph. So we can try to mask out one of the residue, and which we can try to predict the residue type back, right? So this is basically similar to mask language model, but of course defined on graph. So we also actually define some more like some task specifically trying to preserve the geometric information. For example, we also trying to predict the distance between two residues, or the triangles, not triangles, the angles between two edges on the residue graph, or even the torsion angles between basically four consecutive edges, right? So these are the torsion angles. So by defining this kind of like more like geometric inspired task, we hope the geometric encoder we trained are able to extract the geometrical features out of the protein structures. Okay, and then we show that the 3D structure Pretraining based methods actually is able to outperform the sequence based method. The details. So if you're interested in this, you can read this paper, which is now available in archive. So this is the one project I want to mention in this space. Okay. Another project I want to briefly mention, also related to protein reputation learning, is this latest paper, which is gonna appear in this year's NeurIPS. Okay, because as you know, like actually, of course, nowadays, like in the machine learning community, there's huge interest in developing different kinds of techniques for proteins, like for protein understanding, for protein reputation learning. But one big challenge in this direction nowadays is like we do not have a unified benchmark to evaluate the performance of different models on different tasks, right? And we actually already have already seen this in many areas. Like for example, in computer vision, actually the ImageNet dataset actually really like did some foundation work, right? Basically to push the field forward. So we also seen similar case in natural language understanding. For example, in NLP domain, so we have seen like the group benchmark they said, right, has really inspired a lot of like basically ideas, and also track the progress of deep learning models in this domain. But then when we started to work in this area, we realized that okay. So in this direction, we actually do not have a really like a very high quality benchmark to evaluate the performance of deep learning for protein understanding, and that's why like started last year. So we started this project. So we construct a bunch of like different and also diverse tasks for protein understanding, including like protein function prediction, protein localization prediction, protein structure prediction, protein interaction, and the protein ligand interaction prediction. This like 5 different type of tasks. Okay. And then for each task, we actually also, maybe I didn't put the details here. And for each task, we also basically benchmark a bunch of like different methods, including traditional more like feature engineering based methods, and also some latest methods based on pretraining, pretraining and fine tuning. Okay, so that for people who are really interested in this direction, so you can start from our benchmark. So you know what are the most important tasks in this domain, and what are the current state-art methods. So you can focus on developing new methods. Okay, so I will not go to the details. You can read this paper for more information. Okay. I probably, due to the time limit, I probably do not have like too much time into the second part. So maybe I can quickly introduce a high-level idea. Okay. So as I said, like in the drug discovery space, of course, the single molecules and single proteins are very important. But beyond that, the interactions between the molecules and also the interactions between the molecules with other biometric entities are also very important. So this actually can be organized as a big biometric knowledge graph. For example, here's a knowledge graph of like a disease, drugs, and proteins, right? So as I said in the beginning, so this biometric knowledge graph is very important in a bunch of like applications like drug purposing and also target identification, right? And of course, for all these problems, actually the fundamental problem is how do you do link prediction on graphs or on knowledge graph, right? So I will not go into details, but basically I want to say here actually. So link prediction on knowledge graphs on biometric knowledge graph is a very fundamental, it's a very important problem in this domain. So in our group, so we have been working on like different kinds of like link prediction techniques or reasoning techniques on graphs, on knowledge graphs, including like embedding based methods like rotate E, neural symbolic based methods, and this is a new work along this direction developed in my group. So this work is called like a neural Bellman-Ford networks. So the essential idea of this model is we want to combine traditional more like task-based methods with new networks. Okay. So due to the time limit, I probably will skip the details, but you can, if you're interested, you can read this paper. So this is a work published in last year's Neurons. Okay. Okay. So finally, I want to spend a few minutes on the TorchDrug or TorchProtein system developed in my group. So which is a very comprehensive and a general machine learning system specifically for drug discovery. Okay. So the TorchDrug system was released last year. So it's an open source machine learning framework for drug discovery based on a bunch of like important machine learning techniques I've already covered in this talk, including like graph machine learning, graph neural networks, geometric deep learning, and the knowledge graphs, deep journey models, and reinforcement learning. So it has already like covered a bunch of like a lot of like important tasks in this space, including like molecular property prediction, pretraining molecular repetitions or self-supervised learning on molecules, de novo molecule design and optimization, reaction prediction, and retrosynthesis prediction. Okay. So the good thing about this framework, as you see, like we already benchmark most of the important tasks in this domain, right? So we already done all the data pre-processing. So basically, we will like minimize users, domain experts. Suppose you are a machine learning researcher, you want to work on drug discovery, right? But of course, maybe you do not have like a lot of like domain knowledge. So by using this framework, so we're really trying to minimize users' domain knowledge, so that you can focus on developing new algorithms for some important tasks in this domain. Okay, so this framework was released last year, and you can see for this framework, it's mainly for small molecules. Okay, and as I said, like starting from last year, so we really like I think shifted a lot of our focus from small molecules to proteins. Okay, and that's why like actually maybe 1 week ago, and we released another system called like TorchProtein. So TorchProtein basically a specific machine learning system for for protein design or for protein reputation learning. So a good thing about TorchProtein is that actually is totally like unified with the TorchDrug system. Basically, now we have a unified machine learning system which could like model both small molecules and proteins, right? And then so now in the TorchProtein library, so we have a very unified data structure to represent the proteins, like either based on sequence, based on the residue graph, or based on the full atom reputation of proteins. And then we also release some sequence-based like protein reputation learning methods, and also the structure-based protein reputation learning methods I just introduced. And this is actually a big joint effort with a bunch of like industry partners, including some of our partners at MENA, like NVIDIA, Intel, and IBM. Okay. So due to the time limit, so maybe I want to quickly wrap here. So basically, I think nowadays we really see a huge opportunity for AI in revolutionize the drug discovery field in many ways, in particular in accelerating the process of drug discovery, and also increase the success rate. And also, like in the space of drug discovery, many of the most important data is small molecules, proteins, or their interactions, right? And their interactions with other biomedical entities. So they can be either represented as a small graph, a 3D structure, or a big knowledge graph, right? So for all this data, so that's why we see a huge opportunity for graph neural networks, geometric deep learning to analyze those data. Okay, right. And then so in today's talk, I'm basically cover some graph-based methods and also some geometric deep learning based methods to deal with 3D structures. Unfortunately, I don't have enough time to cover some of our recent work based on knowledge graph reasoning for dealing with like biomedical knowledge graph. Okay. So that's pretty much all I want to say. So thanks very much. If you have any questions, please don't hesitate. Thanks very much.
Thank you so much for the great talk, Professor Tang. There's a few questions in the chat. You can start with those, and for those who have questions, please raise your hand, and Professor Tang will take them after solving the question in the chat.
Okay, so Jake White says, ask, in your opinion, what is the most important ingredient in automated approaches for drug discovery? Domain knowledge, model architectures, or something else? I think it depends on who are you talking to, right? For AI researchers, for sure, I think domain knowledge, right? So what are the most important tasks? What are the most important and frequently used data sets? So I think definitely domain knowledge. So model architecture, I think maybe that's not a big deal for machine learning researcher, right? But for people, more like for chemists and also biologists, I think domain knowledge maybe is not important. So in their case, model architectures, right? If you, of course, and if you can develop some like AutoML for them, I think that would be ideal. So I think it really depends on who are you talking to, right? So AI researchers, like, and also biologists, chemists may have different needs. Okay. Charlotte, do you plan on releasing the weights of the pre-trained geometric structure representation models? I think we have already released that in the TorchProtein library. So if I believe we have already done that. So if we haven't, you can raise an issue in the TorchProtein GitHub. Okay. Joseph, regarding the self-supervised learning project, did you also notice an effect of using this expanded self-supervised task set on the sample complexity required for pre-training, or was the primary difference in post fine-tuning performance? I'm not sure quite understand. I understand this question. Should you notice an effect of using this balance?
What I meant was, do you notice that the models take significantly longer or shorter to train when using many tasks to train your self-supervised models, or compared to the mass language baseline that you alluded to?
You mean in this protein, in this pre-training method? These rates compared to this mass language model one, is that what you meant? Or I mean, in general,
exactly.
like if you do like self-supervised learn, yeah, for sure, because like this residual type prediction is relatively like an easy task, right? And this distance prediction and also angle and diffusion prediction, actually the complexity, so like the distance here, okay, is basically the complexity pretty much the same as like the number of edges on the graph. This one is still acceptable, right? But if you look at the angle and especially diffusions, the complexity is much higher for sure. Yeah.
Okay, thanks.
Although when working with proteins at the atomic level, nodes and atoms, would it be more useful to adapt protein representation methods, or rather stick to the right? So that's a good question. I mean, basically, to model proteins, right? Most of the current method is now actually in the residual level. So the main challenge for actually, like the main challenge of like to represent the proteins, or the main challenge to model proteins at the atomic level, actually one of the big challenges is actually the complexity, because like proteins are very big, right? So for example, for some big proteins, you have like 500 residues, right? And each residue you have also many atoms, right? So if you represent proteins as atom graph or atom 3D structures of atoms, right? You could have like quite a few thousand atoms for each protein. So the complexity of doing that is very very high, and that's also that's one of the challenge. Of course, you also there's also there's also actually brings a lot of challenges to your geometry deep learning methods, because you need to learn a good geometry encoder to encode a few thousands of atoms, right? That's also another big challenge, and that's why nowadays actually for most of the methods to model proteins, we actually use residual level graphs. Right. Of course, I think there are also some latest method. Basically, okay, actually we have some like multi-granularity repetitions based on residual level and also atom level. I think I've seen some work on this. They could also be beneficial, but in general, I think representing proteins as residues and still the most common way. Yeah. Oh, I think maybe so. Jian on the diffusion-based methods, right? Okay, let me take a look. Protein structure. Protein diffusion compared to GeoDiff. I haven't read this paper yet. Oh, I think in I think maybe oh, I just noticed this paper. So this is a very latest paper
Yeah,
done
I was
by.
actually trying to look into the references, and I failed to find GeoDiff, and I was just trying to compare the the section 3.2 in which they elaborate the diffusion model that they've used. I pretty much find that it's kind of on the same line of work, except that I was just seeking more clarity in terms of why I should prefer GeoDiff when I go for molecular structure prediction as compared to their work.
Right. So let me clarify this. Okay. So first, of course, GeoDiff is the first model we developed we developed the first diffusion model we developed for molecules. Of course, but when we developed GeoDiff, we mainly applied to small molecules, and that's why I think later it's not surprising there are many follow-up which applied GeoDiff or similar diffusion-based models to proteins, right? So that's one difference. So GeoDiff is mainly applied to small molecules. Of course, the same idea can be applied to proteins, and that's why there's some similar work like this. Okay. So another thing I want to mention is that for GeoDiff, we actually mainly work on predicting the 3D structures. I think for this paper, I'm not sure this is actually I'm not sure whether they're also trying to solve the task of predicting the 3D structures of proteins as well. I quite doubt that, because if they are trying to predict the protein structures, I don't think I think that no way their methods can outperform AlphaFold2, right? So I believe what they are trying to do is, instead of trying to predict the protein structures, I think that maybe they're trying to generate novel protein structures. So if you look at the abstract, so I think so in other words, they're trying to generate a new set of sequence with new structures. So instead of trying to predicting the 3D structure of a given amino acid sequence, because I said if they want to just focus on predicting the protein structures, no way they are able to outperform AlphaFold2, right? I think they are focused on a different task.
Thanks.
Do we need to have a good background on chemistry or biology to conduct AI research on drug discovery? Ideally, yes, but I think you can always I think you can always because for us, when we started to work on this space back to 2018, we don't have too much background on chemistry and biology. I think you can always start to work on this by learning, right? I feel of course it takes time, but I think it's still durable, right? Especially nowadays, if you see you can check the papers submitted to this year's ICLR. There are many papers about molecules, proteins, or in general about drug discovery. And then for many of the papers, I mean, as long as you can start from some specific problem, right? That problem, I mean, you don't need to spend too much time to understand the domain knowledge. I think is so basically what I want to suggest is that you can start from one problem. It will not take too much time for you to understand the background of that problem. And once you get familiar with the background of that specific problem, so you can focus on developing new algorithms for that problem, right? But of course, in order to understand the whole field of drug discovery, of course, it takes some time, right? But I think we could always try to learn. Yeah.